Okay, so the first presentation is infrared velocity tracker. We ask that the teams that you're presenting to line up on one of the sides and do the next team, this way we can have a nice smooth transition. So team 1, or actually team 21, infrared velocity tracker.
First of all, I want to thank you guys for coming out today. I hope you get to see some really cool designs and see what UTD has to offer. My name is Mike Watson. This is my team, Nick, Joel, Wong, and Chris. Our system is based off an infrared velocity tracking system. So basically what it is you take an infrared video image and you're able to identify, track, and calculate the velocity of the moving target. We broke our design up into 2 semester goals. Semester 1 is focused more on research, planning, and creating some sort of algorithm that will be able to identify and track moving targets. The second semester is going to be more focused on calibration, velocity detection, and putting it all together in a single automated system. So we often get asked the question, so what's the difference between your system and, say, a radar gun? Well, radar gun is a point source device. So basically, you point at something and you get its velocity. So if you're trying to view this remotely, what you would see is just a display of numbers. You would see 50 miles an hour, 60 miles an hour. You have no idea what it is that's moving. Our design is actually, you'll see a live video feed in real time. So if you view it remotely, you'll see what it is that's moving, where it's moving to, and how quickly it's moving. Some of the benefits to our design is actually it's a single camera operation. So other systems, they'll have like 2 cameras to calculate depth, or they'll have a camera in conjunction with the radar gun. Well, our design has neither of these, so there's no extra parts. So there's less moving parts. That means the cost goes down. Some other benefits is actually we're going to try and get it to run in parallel, so it can run multiple multiple cameras on one embedded system. So that'll break down the cost as well. Back to our semester 1 goal, we actually were able to meet our first goal. We did some research and we're running some demos in MATLAB under Windows. And we quickly realized that our embedded system is going to be running in a Linux environment and, writing in languages such as C or C++. So we did some research and we found some open source libraries called OpenCV, and we get full credit. We actually went with OpenCV, and it's open as free under the BSD license agreement. So we were able to build upon those libraries and actually create an algorithm that did what we wanted to, was identify and track moving targets. So these 3 images right here are actually pictures of our algorithm running. These were taken right outside the TI auditorium here. This first frame is actually Nick's car. It's entering the frame. And this is a filter applied to, in the middle of the video that was running. And so it's only displaying the car because it's the only thing that's moving. And then so we were able to reproduce, in the third frame, reproduce the original image with a rectangle box around the target. So again, the second, and we actually have this running, we have a live demo right outside, so if you want to stop by our poster and check it out, we can show you more how it works. And again, the second semester is going to be more focused on calibration, velocity calculation, and putting it all together in a embedded system. So I'd like to stop right here and get your input, some feedback, some constructive criticism, and any questions you might have.
Its closing rate for the laser gun is measuring closing rate. You appear to be looking at something passing by that has angular sweep to it,
Right.
and not much closing rate. How do you distinguish speed in that?
Well, like I said, the second semester is going to be focused on calibration and velocity detection. So that's one primary issue that we have to overcome. Is going side to side is going to be easy, but coming right at you and leaving is going to be so challenging, and we haven't worked it out quite yet.
Okay.
Who did what?
I did a lot of programming. Actually, we have 3 EEs and 2 CEs, but we highly contend that an engineer on the most fundamental level is someone who sees a problem and solves it. So we all did coding. Chris did a lot of the research. Paul did a lot of the overlapping video overlay. Joel did a lot of the research as well, and Nick did a lot of the programming, and I did programming as well.
Do you expect any dilemmas with one object going one way and another object going another way?
Absolutely not. Actually, we have tested that, and our demo can actually differentiate between 2 objects moving in different directions. Do you have time for student questions? Or?
I didn't know if we were allowed to ask questions or not.
Yeah.
To actually detect the object is moving, you just, you compare the previous frame to the next frame, does that really give you the sole information that?
Basically, more or less, it's called sequencing. So it's exactly what you do. So you capture it frame by frame. You compare your current frame from your previous frame and subtract the background. So what you're left with is only things that are moving. There you go.
What's the frame rate?
The camera that we're going to be using is 30 frames per second. We don't have the hardware. So what we did is we used a webcam with the same frame rate, which is 30 frames per second.